Thanks. Yeah, I don't know whether they will see me. Okay, so hello everyone, either if you are here or online. So this is the first theory of the semester. The first theory where we all can meet in person, but of course you can also join us via Zoom. We will have today Eivind Schneider speaking about differential invariants of Kundt. And then next time, I guess I will be speaking about summer school I've been on. So I will have a topic about integrability and deformations of integrable models. But I'll send an email after I made the abstract and title. And so I guess that's everything. So feel free to shortly introduce yourself and we can start that.
Yes, so thanks a lot for the invitation. Thank you for coming. My name is Eivind Schneider. I'm currently working in Strasbourg as postdoc, but I will soon be finishing, and I will go back to my hometown Tromsø in Norway, where I will start another postdoc. So the talk is about differential invariants of Kundt layers, but I didn't really get a strict time limit, so I decided to make a really long introduction. Hopefully that will be useful because I suspect that what I will talk about is new to maybe most of them. I'm not completely sure. So the program is like this. I will start with a motivating example. Actually some history. Then I will look at a very simple example of algebraic group actions. Invariants. And then we'll go to a very simple example involving differential invariants, which is the main topic, just to get a feeling for what this is. And then we'll give a summary of the general theory, which is quite heavy geometrical framework, but I'll try to make it quite as simple as I can, but still be honest. And again, we will look at the main example, which will title to this talk. So motivation goes like this. Of course, I guess you all know this. In 1915, Einstein proposes the new theory of gravity. It says that space-time is a four-dimensional space with a metric satisfying Einstein's field equations. So now, of course, we want solutions. Maybe the most famous one, I think one of the first ones, is Schwarzschild's solution. Describes the gravity around a spherical object. And people continued finding solutions in 1921 and 22. Heinlewe and Gullstrand find another solution, things like this. This also has this spherical symmetry, and they use it to argue that there must be that Einstein's theory must be incomplete because, well, which one should you choose? Then more years pass, and we go to 1933, and then Lemaitre discovers that these two metrics are actually the same, just written in different quantities. So it's quite funny that for almost more than 10 years they thought it was different solutions, but it's actually the same solution. And this is a perfect example of the kind of problems I would like to discuss. So the general picture is something like this. We have a partial differential equation, for example, Einstein's field equations. We have a set G of transformations that act in space of solutions. And in this example, it was like all smooth coordinates transformations. And of course, many physical phenomena and also important mathematical structures are described by differential equations. And this is just one example. So we have the general problem of trying to understand the space of solutions, modulo of this. And this is quite a difficult problem because in general, this space is very complicated, and this actually may be very complicated. this may also be described by the differential equation in the general case. So, and both are infinite dimensional in general. So, how can we describe this space? And we will approach this problem through finding a generating set of scalar differential invariants. So let's warm up by looking at a very simple example of algebraic groups. So no differential equations yet. We just have a manifold R3 together with a one-dimensional group. It's just non-zero real numbers. And we have multiplication in this group. And then they act like this. So you take just you multiply each coordinate by
dilation.
Exactly. So what are the orbits here? Should be quite easy to see. There's one special orbit, which is 0, because whatever you multiply 0 with just is 0. And then the others are just lines going through the origin. And yeah, you also have -1, so the full line. So these are orbits, 0 and one-dimensional linear subspaces without 0.
So I guess it's cut lines, more or less.
What?
It's cut lines. It's not the full line.
Yeah, sure. They don't contain 0. Yeah, and so this is the quotient or the space of orbits. So RP2 is just one-dimensional linear subspaces and then also 0. And this is not a very nice space. In particular, it's not Hausdorff, which means that well, any open set contained in this orbit will contain the whole space. So this is a general problem that you get for even this simplest type of equations. But we can solve it by just removing some small sets from our manifolds. Then what we end up with is something very mixed up. It's an algebraic variety. So yeah. And just say a few words about invariant functions. So we say that a function on M is P invariant if it is constant on the orbits of the dimension. So to be a simple exercise to define them, we'll just show them to you. Here are two invariants, x divided by z, y divided by z. If you know some geometry and it's projective space, these are normal coordinates in the space. So we already knew this. We can also notice that we had a three-dimensional space, one-dimensional group action, and 3 minus 1 is equal to 2. So we need two invariants to separate the orbits. They parameterize the orbits. In many cases, it's easier to work with the infinitesimal algebra vector fields instead of the group action. What we can do then, we can take this vector field that essentially describes the same action, and then with respect to this, invariants are those that are constant when moving along, when differentiating along it. So, or no. Yeah, there should be constant, so the derivative should be 0. And it's again an easy check. You can verify that these invariants satisfy these equations. And often this is a good way to try to find invariants, to solve these linear equations. Yeah, so this was just a very simple example to get into this way of thinking. Now we'll go to differential invariants. And again, I tried to choose the simplest example I could think of. So it's supposed to be an equivalence problem, and the first equivalence problem I learned to solve was that of triangles in the Euclidean plane. That's quite easy. You can just to get two angles of the triangle. No, three. What we need? Two angles and a side. But now we'll look at functions. So we consider the Euclidean plane and then the group of Euclidean transformations. So we have rotations and translations in the plane. It's a three-dimensional group. Okay, and we consider the space of smooth functions in this case. So this is really, it's a complicated object. It's infinite-dimensional and quite difficult to work with. It would be even worse if we had a differential equation constraining these functions, which we will add later. So now the transformation group induces an action on the functions in the Euclidean plane. So we say that two functions are equivalent if one can be brought to the other by Euclidean transformation. So in order to determine when two functions are equivalent, we will find a set of invariant quantities for this, and so-called the scalar differential invariants. So yeah, so I said the space of functions is complicated, but since we're working with smooth functions, at least we know one thing. We know that the functions have a Taylor series. So we'll work with that, and we can see we'll actually now just restrict to the second order Taylor polynomial. And the transformation group will also act on this. It's kind of the obvious way. And of course, in general, the coefficients A0 to A2 will depend on the point on which you take the Taylor series. So using a translation from our group, we can move our point x0, y0 to 0, 0, simplify our polynomial a bit. Okay, what more can we do? Well, we cannot use any more translations because that will ruin these nice things. So we have to use rotations. And we can use this rotation here. We try to remove the coefficient of x. But we notice that this requires that a1 plus a2 is not equal. And then if we do this, we get this nice polynomial. And now we cannot do anything more with this. Okay, so this means that what we are left with, these coefficients, they are invariants. And they are actually what we will call differential invariants.
No, je to jedno. Já mám tady špagát.
Is there a question?
Yeah. No, so you turn up. Is it better now? Mika?
Oh, maybe.
Okay. Yeah. So we get these invariants. So these are the coefficients of our normalized Taylor polynomial. And we can consider them as functions in the space of second degree Taylor polynomial. Moreover, we can see that actually we can simplify this a little bit. We don't need this square root, because if this is invariant, then also this square is invariant. And since this denominator here is basically this invariant in all cases, we can remove them. So the numerator will also be invariant. Yeah, so let's simplify our life a bit and use these 5 invariants instead. Now, since they are since an algebraic combination, well, these are invariant, they generate an algebra. Okay, this kind of trivial statement. And moreover, recall that all of these coefficients, A0 to A2, they depend on the point, which also is our base point. So when and in fact, they are defined like this. So they depend not only on the point, but also on the function f. If f is fixed, they are functions just on R2. So we'll use this notation just to clarify that when f is fixed, then they are like this. In general, they are just functions on the Taylor, on the space of Taylor polynomials. These are functions from R2. So if two functions f1 and f2 are related by a Euclidean transformation, then first of all, the functions I0 f1 and I0 f2 must be equivalent. And of course, the same for all the other invariants. It's still not so easy to compare, but what we can do for a generic function, these two invariants I0 and I1, they will be independent functions on the plane. And this puts a condition on f, but most functions that satisfy this condition at this point. So we can use I0 and I1 f as local coordinates, and we can express the other three invariants in terms of them. Because they will also be functions in the same type. And we get these three functions alpha, beta, and gamma. And they are independent of the choice of representative in the equivalence class. So if f1 and f2 are locally equivalent in the domain, where these I0 and I1 serve as coordinates, then they will determine the same functions of beta and gamma. And these you can just compare directly. So I think we have an example here. For example, we have these two functions, x squared plus y and x squared minus 2x plus 1 plus y. It's a very simple example. I think you can figure out how they are equivalent. But you can also use the invariants. So if you compute all these invariants for these two, you'll see in both cases that I to A will just be constant, I to B squared will be a function of I1, I to C will also be a function of I1. It's the same for both of them. So if they are equivalent, then these must be the same. It's not clear yet that if these are the same, then they are equivalent, because we must be sure that the invariants are sufficient, that they generate everything, or that they generate all invariants, or that they separate the orbits. So yeah, and another way to view it is you can consider these pi invariants, you can restrict to some function f, and what you get then is two-dimensional parameterized manifold inside of R5, which we can call the symmetry. And then if two functions are equivalent, you will get exactly the same submanifolds. So yeah, and then you can just, like, if they overlap, then they are equivalent in some spots. So equivalent functions give us the same signature manifold, and conversely, if the invariants generate a whole algebra of invariants, then the signature manifold will also completely distinguish between non-equivalent functions, matrix manipulation. So, and in this sense, the signature manifold solves the equivalence problem. So now comes the fun part, because, well, I said you get two-dimensional submanifolds in R5 in this way, but you cannot get all two-dimensional submanifolds in this way, because they are restricted by some differential equation. And basically, this differential equation is what we call the Gaussian equation, and the solutions to this equation corresponds to equivalence classes of solutions to the original problem. So,
can I ask? I understand for illustrative purposes you took up to second order derivatives, but you say there's only two invariants needed. So why couldn't we just take to first order? Why do we look at it 5-dimensional?
well, it's because I really want these functions. So how do you?
Okay. So you could also go to third order, and then you just get more functions.
You will get 4 more invariants,
Yeah.
and you will get 4 more functions. But it turns out that you don't need them. They are kind of superfluous.
Right.
Yeah, but you should check this to be sure. Or you can trust me. Yeah. Did that answer your question?
More or less.
Yeah. So the quotient P. Yeah, and also, if we try to normalize the 3rd degree Taylor polynomial, we'll get 4 additional invariants. Okay, but it turns out that these can be generated by the previous ones. Of course, not by algebraic operations, but by derivations. So it goes like this. Again, I just need to simplify my computation a bit to not make it that expression is too big. So we'll just call this A is E, G, H, and K. And we will think about G, H, and K as functions of A and B, as we previously did. And again, we assume that these dA, HDB, or A and B are independent functions. Then they can be used as coordinates, and we can actually differentiate G, H, K with respect to A and B to produce 6 new invariants. So since all of the things are invariant, both the results should also be invariant, and that's what happens. And by continuing this, we can in fact generate all invariants. And just to show here, so if we differentiate G, H, and K with respect, well, in both directions, then we get 6 new functions, right? But as I said, we can only have 4 invariants of order 3. When you differentiate, you increase one by 1. So not all of these are independent. There are 2 equations between them. And there are these 2. So these 2 are, they define the quotient equation. Solutions of these correspond to equivalence classes of functions with Euclidean plane up to Euclidean transformations.
Yeah. So how exactly would you get these 2 equations?
You can. It's not clear yet. I think it will be clear later, and if not, you can ask again. Because this was a simple example. I don't expect this to make full sense. I wanted this to be a very simple example that you think you understand, but maybe it's not as easy as you thought. And now I want to kind of develop the language that we really need to properly think about this, because I didn't do that yet. Yeah, and just to continue, or to finish this simple example, let's add a differential equation. So I took this very simple Laplace equation. I could have taken basically anything. It doesn't matter if it's linear or not. And then the only thing, it needs to be aligned with respect to the transformations, because that's the problem we're already considering. And you can see if you add I to A and I to C before, then this actually corresponds to this. So if this is 0, then this is 0. So we get this relation when you restrict to solutions of this equation. So invariants are still invariant, but some of them are now dependent. And you lose 1 second order invariant. And we can write down the quotient equations again. They are actually a bit simpler because we have 1 invariant plus. So this is this describes equivalence classes of solutions of the plus equation with respect to equivalence transformations. And the nice thing is you can do this without knowing a single solution to this equation. So you can talk about the quotient space of solutions without knowing the solutions. purely, well, mostly algebraic. For it consists of algebraic computations, and also in order to find the invariants, maybe you need to solve some linear differential equations. Okay, so that was the kind of introduction. Now I would like to try to develop the language properly. This is maybe the most difficult part. But if I lose you, then you should start following again when I go to the next section. So the general setup is that we have some fiber bundle, and we are interested in sections of some fiber bundle. Examples, for example, a space-time metric is a section that is symmetric around a full-tangent bundle, locally given by time functions, or can, as we did, we consider a function on M, a section of the trivial bundle, one function, or for example, if we're interested in fluids, we can consider sections of the tangent bundle as the fluid flow, and can even add more thermodynamic quantitative fluids here. So just main point is we are interested in sections of a bundle. And usually the sections we care about are constrained by some set of differential equations, such as functions, field equations, or other Stokes equations, and so on. And usually we also have set of geosymmetries acting well, either on M or E, but usually both in some way. So we have some symmetries that take solutions to solutions, and we would like to be able to distinguish equivalent solutions and also perhaps describe the space of equivalence classes. Yeah, so in general relativity, for example, G is the pseudo-group of diffeomorphisms. And as we know, the Einstein equations are invariant.
And the word pseudo in this context?
The word what?
Pseudo in this context?
So yeah, because we allow all local diffeomorphisms.
So you don't know how to compose two local diffeomorphisms always.
Not always, yeah. You need them to have proper domains and columns.
That's the pseudo.
Yes. Yeah. Well, actually, the theory I will talk about it holds for so-called least integers, which are transformations that are solutions to some special system of differential equations. So they will be, in general, local solutions to some different system of differential equations. In general relativity, you allow all coordinate transformations, so it's a trivial equation.
Okay, there's also a notion which is called groupoid.
Yeah, I'm not very familiar with that.
So if I remember correctly, the groupoid is where you say that the two elements with multiplication might not exist. But if it exists, then it has to satisfy the usual associativity.
Yeah. I'm not sure exactly how they relate. There's probably an intersection between these notions. But yeah, I didn't want to put too much emphasis on this. So, but the thing that you remember is that transformations can be local. If they kind of overlap, then in correct way you can compose them. And also it can be infinite dimensional.
Yeah, of course, if you also require it to be a Lie group, then if it's infinite dimension, there's other problems also.
Yeah. So okay, for example, if you have a system of differential equations, you can compute the full algebra of, let's say, the full group of symmetries on E that preserves this equation. This will always be what I would call a least unique group. It will often not be a lead group, for example, and transformations will usually only be defined locally. So, yeah, and for example, if you have a diffeomorphism on M, you get a diffeomorphism on potential space, because you know how it acts on covectors. You also get a diffeomorphism with symmetric power, so on metrics. And yeah, again, this is one of the equivalence problems we are interested in. So now we will define the space of jets, and this is where geometry starts. So the invariants that we found in the previous example, they were functions on the space of Taylor polynomials at degree 2. For now, we will refer to this as the space of two jets. So if you choose coordinates x1 to xn and u1 to um on our total space E, meaning that if we have a section S, then we can just give the u coordinates of this by n functions. Then we can say that the two sections S1 and S2 are tangents up toward K at point P if they have the same partial derivatives at order K. So K, sigma is multi-types, it just means that we take all possible derivatives up to order K. This gives an equivalence relation on the space of sections. We denote the equivalence class by SPK. We call it the K jet of SFE. So this is a fancy way of basically making the Taylor polynomial of order K at P. And then we define the space of all of Taylor polynomials order K at P, and then their union just runs through all points, and we get the space of all jets of sections or K. So, or the space of Taylor polynomials of degree K. So this space we constructed, it's actually a smooth manifold. It is a bundle over M, and the coordinates xi, uj gives also a natural choice of coordinates on k to pi. So we'll denote it like this: uj sigma, and sigma is root index, and we can see. If you try to count just the number of coordinates, for example, we can see that the dimension is 100% times n plus k choose k. And the coordinates of some specific data is just given like this. It looks kind of trivial, and maybe it looks silly to try to make these constructions, but it's actually quite useful because the goal is to, in the end, be able to think geometrically about solution or differential equations and solutions to differential equations. So, and if we now vary the point P, so like P vary in 1, then we see that if given a section S of pi, which is from M to E, then we can prolong it to a section denoted by jks of this bundle. So we get a map from M to jk pi given like this. So we can also it's a section, and it means that it's also, you think about it as an n-dimensional submanifold inside jk. In the same way that the section S is an n-dimensional submanifold inside of E.
So if I take k to be 1, yeah, then you get, so this will be the first jet. So the n would be the base manifold coordinates, and then m is the target space or the fiber, and then you get n plus 1. So so there's n derivatives, I guess.
Yeah.
And why n plus 1?
Because you.
Oh, that's the zero jet.
That's
That's
the
the
first
zero
one.
jet. Yeah, exactly. Because it works.
So the first one, and then you have n times the number of derivatives in that.
Good.
So let's go back to a previous example. Then the bundle is just R2 times R. Your coordinates x, y, u, and the section is given by a function. So for this particular bundle, then let us use these coordinates. So they just use that partial derivatives basically. And now, if we think about this equation, then the notation hints that we can consider this as a submanifold inside of J2. So it defines a 7-dimensional submanifold E2 inside of J2 pi. And if the function is a solution to this partial differential equation, let's say defined on some domain D, then the 2-dimensional submanifold we get here by prolonging, taking the section prolonging this to J2 and evaluating P, will give us a 2-dimensional submanifold inside of J2. And if F is a solution, then this 2-dimensional submanifold will lies inside of the manifold given by our differential equation. This justifies maybe kind of the meaning of considering this equation geometrically. So we have this submanifold, and if we have a solution, then it defines a 2-dimensional submanifold inside of the equation. If it's not a solution, then it will somehow.
And the domain is in the base.
On the base hand, yes. Or R2. So now let's again revisit the Fourier transformations. Now in the infinitesimal form. So we have two translations along x and y, and we have a rotation. So as we saw that like these transformations induce transformations from J to pi. We saw this when we checked how the second degree Taylor polynomial changed. And so the prolongations are given by multiply x2, y2, z2. The first two, they look exactly the same. They don't act along the fibers of the jet bundle. But this does. So this shows how we get transformation on, in this case, second jets. Okay. And the formula here, it's completely algebraic. Usually I ask my computer to do this. So it's quite straightforward. And we can easily check that you take this and take the derivative of uxx plus uyy is 0, which means that the equation, the plus equation is invariant with respect to this transformation. And how to see this? So so most of these terms when acting on uxx and uyy will just give 0. But if you go here, you see that this will give acting here minus 2 uxy times 1. And then from here we get plus 2 uxy plus times 1. And that cancels with 0. We see the easier with this because there is no x and no y. So these are symmetries. As you see that the action of the Euclidean loop on R2 induces an action on the equation E2. And the differential invariant of R2 is, well, by definition, a function on E2 that is constant in orbits. So now we're kind of back in the picture that we started with, where we looked at this algebraic action on the finite dimensional manifold. We do the same. So yeah, if I is a differential invariant over 2, then all of these equations must be satisfied. I mean, this is just restriction to the equation because we don't care about what happens outside the equation. We just want it to be invariant on the equation. And since E2 is 7-dimensional, orbits are general 3-dimensional, then there should be 7 minus 3 in 4 independent differential invariant storage. And you can find them by solving this system, or as we did before, because they're actually the invariants we found before. So I changed notation a little bit. They're not in terms of A, 0, I1, and so on anymore, but they are in terms of the coordinates in the jets. Yeah, if you remember, we also had a lot more invariants before, but since we are on the class equation, there was some equality between the invariants, so we lost one. Yeah, and a smooth solution of this equation is also a solution of the we take derivatives of this equation. So you can consider also as a manifold E3 inside of J3 pi. We will call it the prolongation of the equation. And now, also here, the group action will remain. We'll have an action of a 3-dimensional group on this, what is the dimension? So it's now the dimension is 12 over 3 equations, so I think the 9-dimensional space. And of course, we can continue this process. So just continue differentiating the original equation, and you get submanifolds for higher and higher in Ji for higher and higher I. Yeah. And on all of these, we can look for functions that are constant for this differential invariants. It looks like never-ending sequence of problems, but it turns out that we can generate all invariants by a finite set. And in order to do this, we need some invariance derivations. This was what I almost talked about previously. So we should differentiate along A and B, and this is what we should do. So an invariant derivation is an invariant operator of this form. So these are the total derivatives. Dx takes u to ux, it takes uxy to uxxy. So it's kind of obvious how it acts. And these A and B are just functions on EI function I. It's not clear a priori how high we must go before we find some interesting invariant derivations. So one pair of such operators are these ones, called hat partial I and hat partial J. So we take the expression of this form and we try to apply it to I and J. And we require, just to remind you what I and J are, it's these two simple invariants. And we require that this should be 1, this should be 0, this should be 0, this should be 1. We recognize that gives like the partial derivatives along I and J. And if you restrict to a solution of your equation, that's exactly what it is. But we haven't done it yet, so you kind of play around with this without restricting to the solution. And you can solve this, you get these nice formulas. So, and now when you have these invariants and these derivations, you can, I think what you asked earlier, how do you find these equations? Well, you start differentiating with respect to this, and look for relations between them, symmetries. So you will see that if if you apply these two invariants to the three, or in this case, actually the two other invariants K and L, then you get something in order 3. Okay, but not all of these are independent. So you can just, it's an algebraic computation, just find relations between them. And then you end up with quotient equations that I showed you.
Just a simple question. The number of the invariant derivatives should be equal to the dimension of the base space.
Usually, yes. There are, well, yeah, I think so. There may be some very strange cases, but it's almost always like this. If you have some very strange differential equation, I guess something else can happen, but yeah, usually not. But I actually think that in the case that I'm showing, like in the end, you don't actually need then we have four-dimensional space. And we have four-dimensional derivations, but you don't actually need all of them to generate all invariants. It's not in 3. That's not really a situation. Yeah, so this is kind of the result from this. So the algebraic differential invariance and the Laplace equation with respect to the group of equivalent transformations is generated by these four invariants and two invariant derivations. So let's just summarize.
Sorry.
Yeah.
Just ask you a favor to get closer to the microphone because yeah, I'm going to ask you a question, but I can't hear you so clearly.
Okay.
It's not actually a bad sound. Well, my question is, I've never studied the jets. I mean, I studied just some basic about the fiber bonds and so on. So I'm trying to figure out whether we can use the Frobenius theorem for these jets to know if there exists some solution of, you know, high order partial equations.
If there exist solutions, or
yeah, I mean, my question is just basically, can we use the Frobenius theorem also on jets?
sure. It was, so I talked about the differential invariance here, and it used to be kind of the standard approach in differential invariance that since you have a Lie algebra of action on the space of jets, the Lie algebra of vector fields defines the distribution here.
Yeah.
And it's integrable because it's a Lie algebra.
So we already know that it's integrable, so we don't need the Frobenius theorem basically.
Well, you can use it. So if you have an integrable distribution, you know that Frobenius. Well, I don't know if you. I would use Frobenius theorem to show that the Lie algebra of vector fields actually gives an integrable distribution. And in this case, you can see that that it actually gives you the invariants. Like the invariants are the parameters in this on the foliation you get this integrable distribution.
All right. Okay.
Then, so
Thanks.
did you have another question or something? I didn't fully understand your question.
No. Well, okay. It's more or less okay because you say that we have a foliation. The distribution is integrable, so basically that was the point, more or less.
Yeah. You actually have a different distribution which I didn't mention. So on this on this equation EK, for example, there is a distribution called the Cartan distribution, whose integral manifolds correspond exactly to solutions. But this is non-integrable in general. So
okay. Okay. Thanks.
Okay. Yeah, so differential equation over K sections of a bundle gives a submanifold K in JK. Okay, the transformation on the total space of the bundle lifts uniquely to JK pi, and if it preserves the submanifold EK, we call it a symmetry. So if it takes points inside of JK to points inside of JK, it's a symmetry. Yeah, well, in EK, points in EK, it's a symmetry. So for a least supergroup of symmetries, we can consider the equivalence problem, and we approach this problem by considering a G action on each of these finite dimensional manifolds EI for each I. And yeah, more specifically, we will find the scalar differential invariants.
Can I ask?
Yeah.
So are all of these actions defined by just one action and maybe just prolong that action, or do we have to define the action on all the?
No, you prolong. It's unique. It's unique. So it's like exactly the same way as we computed the action on the Taylor polynomial in the beginning. We have no choice. So it's exactly the same. So it turns out that the algebra of differential invariants is finitely generated. And this is a general theorem. It goes back to Lee and Fessa. And so there are two statements here, basically. So first, the algebra of rational differential invariants separates orbits in general position. I think, so I took out some of the conditions because if I write the full thing, it will take half the page instead. But this is kind of making it, you need to put some conditions on the equation, but almost all the equations that people care about satisfies this. So for the details, you can go to this paper. So first of all, yeah, rational invariants are enough to separate orbits, and the algebra of rational invariants is generated by a finite number of differential invariants and invariance derivations. That's what we saw in the example, but it's a general. Yes. So it's kind of the fundamental theorem of scalar differential invariants. I mean, there's a lot of history, so many people have been working on this, but the last, I would say, significant contribution is by first people from Lorentzian. So now we are ready to go to our example, and it's about Kundt waves. So Kundt waves are four-dimensional Lorentzian manifolds with a metric which in some coordinates takes this form. Okay, we can give a coordinate-free description, pure radiation space-times Petrov type 3 or higher, admitting a non-twisting, non-expanding null congruence. It's quite technical, so it's much easier to just look at the coordinate expression, and that's what we will do. And they belong to the class of vanished DSI spacetimes, which means vanishing scalar invariants. It means that they're polynomial curvature invariants, which are the complete contractions of the Riemann tensor and its covariant derivative vanish. So all invariants obtained from the Riemann tensor and its covariant derivative will vanish. So you cannot use these invariants, which are in fact scalar differential invariants. You cannot use them to separate these symmetries. So we need some other invariants. And that's what we will find. Yes. So,
but the curvature tensor itself does not vanish.
I don't remember. Not necessarily.
Right, so it's only something.
No, it doesn't. It doesn't. Yeah, I will show you the Ritchie flatness condition soon. So our main question is when are two Kundt waves with metric of this form locally isometric? So yeah, we can detect the history first. So the Ritchie flat case here is Ritchie equals 0. That's non-trivial condition. So that answers your question. It was studied earlier. And they use the Cartan-Carteda algorithm. Basically, yeah, it's very different. At least it looks very different from what we're working here. We will not consider this equation, we'll just consider general Kundt waves. It's actually not much of a difference, and our results can be restricted to this case. And our approach is, as we did already at one time, is to directly compute the full algebra of differential invariants. Okay, so, but now we restrict to metrics of this form. So the action, the group action or pseudo group action is not, it's not all, we don't allow all the morphisms because they should preserve this form. This puts some conditions on the transformations we want to consider. And so the least pseudo group G of transformation preserving the shape, G is just the form of G. Is given by these transformations. So now F is a local diffeomorphism of the union, and the transformations are parameterized by one function, one constant and one function. There is also two discrete transformations if you just take y to minus y and xh to minus x minus h. And the linear vector fields is now this corresponds to this translation, and F here is corresponds to F, capital F, but this F is arbitrary. Yeah, and these transformations were also found in this. So now what is our differential equation? I actually forgot to mention. So this coordinate expression, it depends only on one function h, of x, y, and u. Our coordinates are x, y, u, and e. But this function h does not depend on b. That means that we have a differential equation, namely that d derivative of h is equal to 0. It's a very simple differential equation. And if you want, you can also have this equation if you were interested in Richie Platt controls, but now we just consider the simplest case. So it looks like this. We have J0. Didn't even talk about J0, but it's basically just it's the same as the total space E. And in E1, you have one equation, so this space is non-dimensional, the one equation, so this subgroup is x-dimensional. And you can continue this process very easily. So the action of the shape preserving pseudogroup lifts to EK for any k. And we want to understand how G acts in the space of solutions. When our two solutions equivalent. And we do it by finding invariance functions in EK. And again, this is a finite dimensional manifold, and it's much easier to think about. So let us count some dimensions. So this is the formula from before, but adapted to this case. Dimension of J5. And now the number of independent equations defining k is, for example, if k is equal to 1, and we get 4 over 4, that's just 1, that's h equal to 0. And you continue this. And in general, if you just subtract these two numbers, you get the dimension of our manifold k. And this will be important because if you know this and the dimension of the generic orbit, then when we subtract them, it should give the number of independent differential invariants. And this actually we need to do some computations, but we should show that the dimension of the orbit in our position is 4 for k equal to 0, and k plus 5 for k bigger than 0. So the group is infinite dimensional, but It's a finite dimensional power acting on each one, but it grows without points. So the number of independent differential invariants, or K, is equal to the codimensional orbit in general position. This is what we need this counting. So let us see what we get. I just made a table here. This is just dimensional depth space. This is the dimensional equation. Here is the dimensional orbit. So the orbits will, in general, have different dimensions, as we saw in our first example. We had one-dimensional orbits and zero-dimensional orbits, but at most points, the orbits have maximal dimension. And this is what we can see. So we have four-dimensional orbits here, six-dimensional, seven-dimensional. This increases by one each time. Now, if we just subtract these two numbers, we get the number of invariants that we expect. Number of invariants. So 8 minus 6 is 2, 14 minus 7 is 7, and so on. And of course, an invariant over 2 is also an invariant over 1. So here I just split it up. So I say we have one invariant over 1, and in addition to this, we have 1 over 2. In addition to this, we have 5 over 2. So now we know what to look for. And you can try to find invariants by solving these equations. You take vector fields, the derivative of a general function, set it equal to 0, try to solve. And in this case, it actually, I think it works quite easily just by using some differential equation solver and some symbolic software. So, yeah. And you can find this function here in general. So this is general number of invariants or that exist. And in particular, so we have 1 over 0, 1 over 1, 5 over 2, and they are here. So this is invariant over 0. It's just x squared actually, because if you remember that we have some discrete transformations. I think taking xh to minus x minus h. So we need the square here. Same thing happens with this. Because when y goes to minus y, this changes sign. So that's why we have the squares here. And then the rest, yeah, more or less progress. Rational functions as this Lee-Tracer theorem predicted. And we also have these invariance derivations. So now we can start differentiating, taking nabla 1 of each of these, or 2 of each of these. And what we should make sure is that we get the right number of invariants of each order, because we already know what the number should be by the counting. So this is basically for a frame of 4 independent vector fields. You can make the dual frame, co-frame, with this. So it's just some bond forms. And yeah, they are in general independent. So there are some points that you should actually remove from the first iteration. Like we did again in the first example, you threw away 0, and outside is things were not. And it's something similar happens here. So if we write our integers in this co-frame, then coefficients are just this, and we can write it down. And it's quite simple. I0 here, I1 here, here I1 times I2t. This actually suggests to us that the invariants, we don't need all the invariants in the previous slide. Actually, we can make it with just these 3. And this is the result. Algebra rational differential invariance is generated by the second order invariants I0, I1, I2d. and these 4 invariant derivations. And actually, to be clear, I don't think we need the 4th one, but I will do it. Yeah, it's easy to see. Yes, because this only was partial, well, dv, and we know that h will not depend on v, never ever. So when you did start continue differentiating, you will always get things. Well, you basically just 0. Maybe some things you need to check, but that's more or less what happens. So then the question is, how can we use what we know now to distinguish non-equivalent Kundt? What we'll do is to choose 4 independent differential variants. It's kind of similar to what we did before. Then the base was 2-dimensional, we chose 2 invariants as coordinates. Now we will use 4 invariants as coordinates. We can, for example, use these that we found. And then they are independent in numeric points. So this should perhaps be explained, but what I mean by this after D means that if we pick a particular solution or particular Kundt wave, then these will be functions on the base in the 4-dimensional manifold. And this just means that after doing this, they will be independent in general. So kind of it's like this framework of objects, it allows us to all the time work with things without specifying the sections, without specifying the section. This is what it's missing. So, and I can actually write it down for the so d hat or function f, it's dx of dx plus dy dy.
Let's see whether I make it more.
du plus d. It's very similar to the normal version of this, but it's with the total derivatives and not with the partial derivatives. So it's not partial derivatives. And this is just because we didn't specify the section yet. And if we restrict this to the section, you just recover the normal exterior differentials. So now we rewrite the Kundt waves in terms of this horizontal profile given by this. Okay, so Ji, they were differential lines over 2. Now when we take this horizontal differential, the expressions will depend on 3rd order terms. So actually what we get here is some expression, some new invariants Gij, which are 3rd order invariants because we differentiate them once. And these invariants, the Ji's and the Gij's, they will generate the whole algebra in a different way than we found before. But this is in some sense more useful for us when we try to compare things. Yeah, so we get 14 differential invariants here. And now if we restrict the invariants to specific wave, they will be functions on R4. And since J1 to J4 are independent, we can express Gij in terms of them, and we can just compare these functions to check equivalence. Okay. So I decided to end this talk with an exercise for you. Which of the following two players are equivalent. So they were given by function h. Here are three different functions h. Do you have any guesses?
Can you go back to the formula?
Which one? G. This one?
The ones for
Invariants. Well, I didn't show you the GIJs.
yeah.
And this is the reason I didn't show them, because they are horrible. They are huge.
So you should only guess, like we don't have.
Yeah, you should. So you. I don't know. At least for me, I cannot see from this what equivalent, and it's kind of difficult. So we know what the transformation should look like. You can try to adjust your function with a capital F, try to make the transformation. It's not trivial, but when we have this invariance, like it's actually quite easy. At least for this particular case. So I found a case that says to solve to show it to you. But you compute the invariance. So I0, I1, I2B, I2C, and I told you only to show you G1. There are 9 more of similar type, but let's just look at the first one. And I advise to use a computer for this stuff. It's not fun to use by hand. In this case, we get this. And in this case, we get this. So actually from this, I guess, yeah, can you guess? It's still a bit difficult. Because remember, what we need to do is to express G alone in terms of these other four.
And then only the G's have to be equal.
Yeah. H1, we get this nice expression. Okay. H2, this. Nice. So now we know they are not equal or equivalent. Wow. And this. So these two are not equivalent, these two are not equivalent, and we have basically reduced the equivalence problem to like recognizing this algebraic function, and that's not trivial either. But if you go through this, I think you can compare each term. So of course so in order to verify that these are actually equivalent, we need to do this for all the 10 GIJs. But you can see it for one. Yeah, so the conclusion is that the Kundt were given by H2 definitely not equivalent to the others, and it's possible that H1 and H3 are equivalent, and to completely verify this, we need to check the rest of our invariants. Yeah, so here are some references. This last example, main example is based on this paper I wrote with first Eivind and then Kundt. We also have a later paper which concerns Kundt spacetimes. It's more general to us. It's a bit more difficult. So you can also look at this if you're interested. And then Michelle and Immersion, they use this same approach in a more general sense, just generic metrics in relativity theory. And yeah, this is kind of the main theorem in differential models. And I think that's it. So thank you very much for your attention.
Okay, so thank you Eivind, for the talk, and now we will have some questions or discussion session. So I guess feel free to unmute and ask the question, or we will ask some questions. You can also write in chat. Yes, someone should check the chat. Yeah. So I guess I'll stop the recording and we'll just continue with